Okay, so we're going to finish off the notes for today with the last two slides. This one is about a doctor who notices that 22% of her adult patients show higher than usual levels of glucose in their blood. So we have a p-hat of 22%. And a group of researchers then decide to conduct a large-scale study, hoping to estimate the true proportion for the whole population to within 4%. Okay, so to estimate within 4% means we could find a p-hat and go 4% below, 4% above. That's a margin of error. So margin of error is 0.04. With 98% confidence is a z-score. Well, gives us a z-score. So our z-star this time, if we remember from the last problem we just worked, is 2.33. Now, if we hadn't just worked a problem with a 98% confidence in 2.33, we'd have to figure that out. So if we have to figure out what our z-star is, we think about a normal curve, and we're hemming in the middle 98%, and we want to know this upper z-star, z-score, that's associated with this area. If 98% is in the middle, that means 1% is on the lower tail, 1% is on the upper tail. So below the cut score that we want is 99% of the area. So we use our inverse normal command with 0.99 as the area, and we would get approximately 2.33. Okay, so what we have that associates all these numbers and what we're looking for, how many randomly selected adults, that's N, must they test? To associate all those things, we need a margin of error formula. So the margin of error says the margin of error, 0.04, equals z-star, 2.33, times the square root of p-hat, that's 0.22, times q-hat, that's 0.78, over sample size, which is what we don't know. It's what we want to solve for. Okay, so now we need to solve for n. We've got two choices. One is to do some algebra. So I would divide by 0.04, multiply by that square root nonsense, which will turn it upside down, then square both sides, then multiply by 0.22 times 0.78. So we could do the algebra to get n on a side by itself. Or we could, because we're probably going to mess that up or just it's going to take too long, we could type in our calculator solve, type all that in, and then do comma n. Now on our paper we don't want to write this, so what we want to show on our paper is this part. And then what we put in the calculator, we surround it all by parentheses and ask it to solve for us. Because I'm trying to make these videos as short as possible so you have time to do work on your own, if we crunch that out and solve for n, we'll get 582.25. So we need to select and test that many adults. Of course, a quarter of an adult probably isn't available, but we'll need this minimum to get this confidence level and this margin of error, which means we need to round up to the next whole person. So they need to test 583 adults. So we always want to round that sample size up to get a whole number of people or things to survey. Okay, one more slide and we're finished with this one. So just to kind of pull some of these big ideas together, you're always going to get questions a lot of times in your multiple choice that associates margins of error with levels of confidence and sample sizes and how they interact with each other. And you can look at it from one of two ways. You can look at it from the perspective of a picture. So you have a normal curve that kind of governs the universe. You have a margin of error that's associated with a level of confidence. You could have 90% of the area, 95% of the area, and you're estimating some p-hat, and then you're coming out to the left and right with some margin of error to estimate a population parameter. So you can use the picture, or you can use the equation margin of error equals z star times the square root of p-hat q-hat over n, and think about manipulating those numbers. So we'll look at it from both perspectives. So I want to know, fill in the blank, the larger the margin of error, okay, that means the wider this gets right here. So the bigger this gets, the blank, the level of confidence. Okay, so the level of confidence is associated with the percentage of area under the curve. So if the margin spreads out wider, then that means we're getting a bigger percentage inside. So we have an increased confidence level. So that means the higher the level of confidence. Another way you can look at it is from the perspective of the equation. If ME gets bigger, if this side of the equation gets bigger, then for the other side to get bigger, we'd need a bigger Z star. So it would have to be a higher level. For a given confidence level, okay, so if Z star is fixed, the bigger the sample, the blank the margin of error. So we know that a bigger sample gives us a smaller standard error, smaller standard deviation. If we look at it from the equation perspective, bigger sample means this denominator is bigger, which makes this overall fraction smaller. And if we don't change Z star, then this entire right side of the equation would get smaller, so the margin of error would get smaller. So we get a smaller margin of error. You can also think of it this way. As your samples get bigger, your spread in general gets smaller. So if things are less spread out, then we should have a smaller margin of error. All right, third one I think is probably the toughest one to think through. I use the equation for this one. For a fixed margin of error, so margin of error is fixed, which means the right side is fixed. Z star times P hat Q hat over N under the square root, all that has to stay fixed. A smaller sample, okay, that means N is smaller. Okay, if N is smaller, then this overall fraction is bigger. So this part right here, the standard error would be bigger. And in order to offset that bigger standard error, to keep this side the same, Z star would have to get smaller because they have to balance each other out. So if Z star gets smaller and standard error gets bigger, then that overall margin of error can stay the same. So smaller Z star means that we have a less wide area under the curve, which means we have less confidence. So smaller sample, if you think of the big picture, the more people you sample or the more things you sample, the more sure you are that your population parameters estimate is going to be good. So that means if we lower our sample, then we're going to have less confidence. We're going to be less sure about what our results are going to show us. Last but not least, for a given confidence level, a sample 9 times as large will make a margin of error blank as big. Okay, and this answer is 1/3. So if we go back to that earlier slide when we talked about the relationship between multiplying n by something and how it affects the margin of error, if we do square root of 1/9 P hat Q hat over N, so we make it 1/9. This is going to be 1/9 as big because we have 9 times the n. When you take the square root of that, when that comes out, it becomes 1/3. So 1/3 the margin of error is what we end up with. Algebraically, that's not particularly pretty, but you have the rule for that back on an earlier page. You take the square root of your sample size scale factor and then make take the reciprocal of that for the margin of error. So square root of 9 is 3, 1/3 is big. Okay, you have a homework assignment on that next slide. Help each other out. Check your work as you go and have a good day.